need to put a warning.
Okay, so I hope everybody can hear me.
Yeah, Luca, I hear you fine. I think the panelists can also hear you. People are joining.
Okay, so let's give it a couple of more minutes, then we can start. Okay. Okay, good morning, everybody. I think it's time to start. And today we are going to go over the third part of the lecture. First, I'm talking today as a first, and then Frank will come second with the last part of the lecture. So the objective of this lecture is to discuss about using the RISC-V course that we described in quite some depth in the last lecture yesterday, and see how we can integrate RISC-V course and more specifically this open source course into systems on chip, and how to create from the basic work element, which is a core, more complex systems made of multi-cores, and all the architectural and implementation issues that come with this challenge. So let me start with the main concepts that led to the project, whose content I'm describing today in this lecture, and this is called a Parallel Ultra-Low Power project, the PULP. In the context of which the cores that you have seen in the previous lecture have been designed, validated, and implemented. So the idea motivating the PULP project was fundamentally to bring complex computations on sensor signals to the edge, so near the sensors. The typical type of computations that we have these days that are linked to data processing, sensor data processing, are AI type of computations, and more specifically machine learning computation, and even more specifically deep learning type of inference computations. Now, if we look into specifically as a driver example, but this is of course not the only one, but I think it's a very important one. If you look as a driver example, inference of deep neural networks in this type of context, we see from this slide immediately what the challenge is. In fact, as you can see, the amount of operations that are here, you can see on the x-axis, needed to run high accuracy neural networks for signal analysis, classification, and so on, is in the order of the gigaops. So even if we go close to the zero, to the smaller and less accurate neural networks, we still are in the order of giga operations per second. And so if you want to have a reasonable accuracy and high performance, you need to be able to provide giga operations per second. It's neural networks, in a sense, from a computer architecture viewpoint, are a nice workload to work with, because fundamentally they have embarrassing parallelism, so they are highly parallelizable. They are dominated by DSP-like type of computation, so multiply, accumulate typically, and they're also very tolerant to low precision, and they're also quite benign to model reductions. In fact, you can see here that you can move from highly complex models with a very large computation and decrease this the effort required for the computation by an order of magnitude with a very minor decrease in accuracy. So all these characteristics conjure to make deep neural networks a friendly workload for computer architecture. On the other hand, when you want to move this to the extreme edge, you nevertheless have to provide computation capabilities in the order of the giga operation per second. So if we look at the challenge of bringing these operations to the edge, or the extreme edge near the sensors, you see that typically near the sensors at the extreme edge, we have limited computational capabilities. And these are usually provided by microcontrollers. So the well-known ARM Cortex-M microcontrollers like M0+, M3, M4, M4F are the microcontrollers that can be deployed at the extreme edge near sensors because they have low cost, and they are very flexible, so they can be adapted to a very large number of computations, not only neural networks, but many other computations. On the other hand, the problem is that these platforms are not designed and they were not capable of very large workloads. In fact, this plot shows a set of commercial and research microcontrollers collected a few years ago, but the picture has not changed a lot, on a performance versus energy per operation plot. So performance versus energy efficiency. First of all, you see that the microcontrollers, even in the most powerful case, very, very rarely approach the 1 giga operation per second limit, which is what is needed actually for neural networks. Second, besides that, you also see that there is a very clear trade-off here. As you move to more powerful and capable microcontrollers, so these processors are more capable, you immediately lose very significantly in terms of energy efficiency. So your energy per operation goes up exponentially with an exponential improvement in performance. So you see this line in this plot. So what is the problem? The problem is that if you want to high performance MCU near the edge, then you have to pay a lot of power and you lose in efficiency, in energy efficiency. Or if you want to have very high energy efficiency, so low energy per operation, you have to be content with a very limited amount of capabilities. When we want to do near edge processing, neural networks and more, we want to be where the bullseye is. So same energy efficiency as the low power microcontrollers and low capabilities microcontrollers, but also high computing capabilities. So we want the best of the two worlds. Just to give you a feeling, a quantitative feeling, if we could do computations between 1 and 1 picojoule, between 1 and 10 picojoule per operation, then we would be between very reasonable, because this point that I highlight here is 1 picojoule per operation, but that would be here, and 1 giga operation per second. So we would be in this corner pointed by my red dot if we achieve 1 picojoule per operation at 1 giga operation per second. So that's a very nice target. Of course, then we may also want to go beyond that. But this is already something that the current microcontrollers cannot do. And with these capabilities, you could run a high accuracy neural network like Inception V4 at 1 frame per second, 10 milliwatts of power, just to give you the idea. That would be coherent with the budget of an extreme edge microcontroller. How can we do that? So remember from part 1 that we designed this nice microcontroller type of cores like RISC-V, that is our beloved workhorse microcontroller. This is designed for very high efficiency, so it's a processor where we focused a lot on making sure that most of the area was in the data processing part and not so much in the control part or in the overhead due to other things like virtual memory and so on, like we have in Ariane. So we start from our most efficient microcontroller for DSP, which is RISC-V, and we, as Frank showed in the previous lecture, we extended the baseline instruction set thanks to the flexibility of the RISC-V and the openness of the RISC-V IC. We extended the microarchitecture and the instruction set to support things like hardware loops, post-modified load and store, multiply accumulate operations, as well as SIMD operations, dot product, shuffling, bit manipulation, lightweight fixed points. All these instruction extensions are needed to make the core more efficient and suitable for the type of DSP near edge computation we want to do. So at the end, we get a core that is around 40,000 gates, 40 kilo gates, and of which, most importantly, almost 70% of the core is in between the register file and data path. So it means that the overhead for instruction fetch, control, and all the stuff that is not really register file and data path is only 30%. So it's a very efficient core. What is the problem? We also have seen that this core delivers on DSP like neural networks and more general FFT and other processing very well, because with this optimized core for DSP, we actually have 9+ times the DSP capability of the original ISA, and with only 1.6 increase in area with the original bare bones core, with no support for these extended features. So that's very nice. What is the problem, however? What about the GOPS? This core can run at something like 500 megahertz max, even in an advanced technology, and then it cannot deliver the gigaops, the giga operation per second, the giga max per second that are needed for a neural networks, because we are bound to 0.25 giga operation per second with a single core or something like that. So what can we do? Well, we, what the microcontroller industry has been doing is, was shown in the plot in the previous slide, which is essentially moving up in performance, so adding features to the cores. But we already know from our Ariane experience and from the experience done by many other people in computer architecture that trying to increase your computational capabilities with a core that is faster, deeper pipelined, with superscalar capabilities and so on is not energy efficient. We are going to go the same way. So in fact, if you look, for example, for M4, which is ARM M4, which is comparable in performance to RISC-V, you have this type of energy efficiency is shown here. If you go to M7, which is the next step up in terms of performance for the ARM Cortex-M family, you actually get a bit more performance, not even a factor of 2 more performance, but your energy efficiency is 3 times worse. So we don't want to go this way. What can we do then? Well, we have to exploit the fact that machine learning is highly parallel. And then we can exploit the fact that also CMOS logic is actually very friendly to parallel operation. What do I mean by that? If we actually look at the plot that we have here, where we see what happens to performance and maximum frequency and power as the voltage changes, and then we look at efficiency, which is this red set of red dots, we see a thing that is very well known for people that design CMOS logic. It means that you see that there is a very stark trade-off between high frequency and power and low power. So this is the bad news, but the good news is that if you move at low frequency and low voltage, you get higher energy efficiency. So you are more energy efficient when you work at near threshold, close to the threshold of MOS circuits. So what can we do then? Well, we can operate our microcontroller at very low voltage, getting the maximum energy efficiency, and then you want to get the performance up by running several microcontrollers in parallel, because in this way we have a simple microcontroller that is the most energy efficient microarchitecture, running at the low voltage, which is the most energy efficient circuit operation point, and by having parallelism we achieve the performance levels that we need. So that's the concept of parallel ultra low power. Of course, if you push this game too much, then you see your energy efficiency goes down. Why? Well, you know for sure that this is because of leakage. If you go too slow, then your leakage in your circuit start to become the dominant effect, and then you lose in energy efficiency. So there is a point, which is the optimal operating point, which is around the threshold of the transistors, actually a little bit above the threshold of the transistor. That's what we call it a near threshold. And we can exploit this operating point by putting several processors in parallels and exploiting the parallelism of the native application that we are trying to execute on our microcontroller. So from a single core microcontroller, we have to move to multi-core near threshold microcontrollers. So conceptually, this is simple. Now, the rest of the lecture is to explain that in reality is not so simple, and you have to do quite a lot of things to get it to work as planned. So the idea is, let's take several of our RISC-V cores, operate them at low voltage at relatively low frequency, but put them in parallel so that they can do work in parallel. That's very nice. So we make a cluster of processors. So we take n RISC cores, maybe we can start from 2, then to move to 8, 16. So let's consider as an example 4, like in this picture. And we put them in a cluster. We want them to work together on a single task. So, accelerating, for example, a neural network computation. Now, the first problem comes. These guys will have to work on the same data. Somehow we cannot assume that they always have to work on separate split data. So we have to have a way to connect these cores to memories and make sure that they can access the memory in a flexible way, so without being confined to access only a single memory. Otherwise we'll have a nightmare in partitioning the data for each core. So they have to have a flexible access to memory, and at the same time being able to share this memory. So ideally we want to have an interconnect between these two, the memories and the core, such that these memories behave like multi-ported memories. In a way, whenever two cores want to access the memory, they can access at the same time, because if they have to serialize on the memory, then we lose all the parallelism. So we need to provide the capability of making the access in the memory of the cores concurrent and prevent the cores, at least reduce as much as possible conflicts in the access of the memory to avoid serialization. How can we do that? Multi-ported memories, when we have more than a couple of ports, are super expensive and at the circuit level are not a viable proposition. So instead of using multi-ported memory, we emulate multi-ported memory using a single-ported memory in a multi-bank configuration. So we connect the processors that are on the top with several single-ported banks of memory that you can see on the bottom, using a logarithmic interconnect that is essentially an implementation of a crossbar that connects all the processors with all the memories. Now, This crossbar is made with routing trees, and you can see you have a logarithmic number of routing levels depending on the number of memories and the number of cores, as shown here. And then we implement this logarithmic tree with combinational logic so that we can use one cycle to access the memory, and in the second cycle we will get the results back. That's what we call our logarithmic interconnect. Now, how can we spread the addresses in the memory map to this memory? The idea is that we word interleave these addresses. So first word is in the first bank, second word is in second bank, third word is in third bank, and so on. What is the rationale of doing this type of address interleaving? The rationale is that you spread neighboring addresses in different memory banks. So if cores are working on neighboring addresses because they are typically sharing data and splitting the work on a matrix or different rows of the matrix or different elements of the matrix, if they are working on neighboring elements, they will not conflict in the memory. So as long as their address is not the same, they will fall in a different bank, and of course there could be still banking conflict, because if core 1 access memory bank 1 and then at address n, and core 2 addresses address n plus 8, there is still a memory conflict. However, since we have used this word interleaving, we spread the accesses, we spread adjacent accesses over several different memory banks, and we reduce the probability of contention. So it is not a perfect multi-ported memory, but is a good approximation of it. And we have a lot of bandwidth between the processors and the memories. So the word level interleaving emulates a multi-ported memory. In the first cycle, the processor gets across the logarithmic interconnect the so-called request path, and in the second cycle, it gets the data back. So this is a very short and fast latency across the interconnect. And we need to be careful, because the cost of this has to be carefully gauged. All the gates and all the energy spent in traversing this interconnect goes as overhead for your computation, because it's adding cost into your memory access. So it has to be very, very carefully designed. So we spent a lot of time in designing this type of interconnect and highly optimizing them in terms of implementation, digital implementation, and circuit level design. So we have this, of course, open source IP, which is the so-called TCDM. TCDM stands for Tightly Coupled Data Memory Interconnect, which provide access, is a scalable IP, so is a parametric IP, which provide access to from several masters to several slaves. Masters are the processor, slaves are the memories, and implements distributed arbitration, so it doesn't have a centralized bottleneck in the arbiter. It has a combinational handshake as required for a short latency interconnect, so there are no multiple stages, multiple clock cycle when you traverse the interconnect, but the interconnect is traversed in a clock cycle. And it has a deterministic access latency in absence of context, in absence of banking conflict. It also supports atomic access, so test and set access in the memory, which is, as we will see, very important for parallel computing. And thanks to word level interleaving, it reduces the probability of access contention. If you want to control and reduce the probability of contention in a bank, you can use a larger than one banking factor. For example, banking factor of 2, which essentially means double the number of banks compared to the number of masters. This, of course, has a penalty in area, because the more banks you do, the larger is your memory, but there is a trade-off. With modest banking factor increase, like a banking factor of 2, you can reduce a lot the contentions. We also provide similar interconnects for accessing peripherals that have to be accessed by the cores in short latency. For example, a peripheral needed for synchronization of memory copy that we will see soon in the presentation. In this case, there is a difference because peripherals are memory mapped. The interconnect has to provide access to contiguous addresses into the same target port, since the target port now is a peripheral, and all the registers corresponding to that peripheral will be in a contiguous region in the memory map. So we cannot apply word level interleaving here, otherwise our address of our peripheral will be spread to several target ports, which is not acceptable. We have a peripheral with a single target port. So the address multiplexing scheme is not word level interleaved, but the topology of the interconnect is very similar. We also provide an interconnect with similar characteristics that we use to share functional units. What is the main difference between sharing a memory bank and sharing a functional unit? A functional unit is still providing a service like a memory. A memory provides data. A functional unit provides a processing of data. The main difference is the memories have addresses, while functional units don't have addresses, so they are identified by the operations they want to do. So if you want a multiplication, you have to go to a multiplier. So in this case, this interconnect is similar in topology, but the routing from the requestor, which is a processor, to the provider, which is, for example, a divider or a square root unit, is not based on addresses, but is based on the type of operations that you are requesting. And so the interconnect will route the processors to the appropriate unit using the request type. So I want to do a multiplication, and we route the operand to the unit. This routing and arbitration will have to be performed not based on addresses, but based, for example, on number of cores, how the cores are mapped into the various target, which are the units, and which with priorities. So here we use, for example, random arbitration, which essentially means that you map the request to the unit that is available among, and you choose among the multiple requests randomly to avoid privileging a single core, and at the same time, thanks to the randomness, spread out the accesses to several available targets if there are several targets. So these three interconnects have a different input-output behavior because they have a different mapping logic and arbitration logic, but they provide similar services. So they provide an N-to-M connectivity that emulates a multi-ported access. So, for example, to show an example of the last one that is a bit different from a memory network, this is a technique that we use to share the large floating point unit. If you have a floating point unit that does, for example, division or square root, you don't want to replicate this floating point unit for each core. So you can provide this a couple of divide and square root units, and the processors can share them using this type of interconnect. The advantage of this is that you have a better area efficiency because you don't have to replicate this fairly large logic, and at the same time your performance penalty is not so high because these operations are not needed in all the cycles. So to bring back into the architecture, once we have provided these services for sharing memory, sharing peripherals, and sharing functional units, we can get to the next point. The next point is that the memory that you can access locally to the processors is through this interconnect is of course a small memory, because remember, this memory can be accessed through the interconnect in two cycles, one for request and one for response. So this memory cannot be huge, otherwise the access time to this memory becomes too slow. So then we needed to also handle the memory hierarchy, which means that we needed to have a way to bring fresh data into the level 1 memory that we have tightly coupled to the processors inside the cluster, from externally, for example, from large background memories or even external memories or IOs. To do that, traditionally you use caches, but caches in this context are very expensive because of, remember, the Ariane experience. Tag logic, tag comparison, and all the stuff adds a lot of overhead. So we decided to go for an explicit memory hierarchy, where you use a DMA engine, direct memory access engine, to perform copies from IOs or higher level of the hierarchy to the inner shared memory in the cluster using a copy engine, a DMA engine. So the copy engine looks like a master on the interconnect. So it also accesses the interconnect as a master like the processors, and its goal is to take the data from outside and actually copy it inside through the logarithmic interconnect so that the cores can work. Now, this is actually a special design, the so-called M-chan, the DMA is a special design made specifically for the ultra-low power target. Without going too much in details, I want to give you the intuition why it is a special design. The idea is that usually DMA engines, like the ones that you have for in high-performance computers to do remote DMA or PCI Express DMA, all these large DMA engines, they do have some large internal buffers. And the reason why they have large internal buffers, these traditional DMAs, is that they copy data from a very long latency memory, like, for example, an external memory, and then they have to send this data into another memory, which is somewhere else in the chip. And so there is high latency both in the data that is coming in and the data that is coming out. So in this case, they needed to buffer internally the data that comes, because if you don't have internal buffer in the DMA, then you will wait for the data coming in and then have to, before getting new data from your source, you have to wait for the destination to accept the data that you just got from the source. And so you will waste a lot of time. So what the traditional DMA does is it has an internal buffer where it keeps filling it with the data coming from an ingress port, and it's emptying it on the other side of the buffer, so with the FIFO policy, toward the egress port of the DMA. In this case, we don't have the problem. Why? Because our DMA is tightly coupled, remember in the previous slide, with a very short access latency to the egress, to the destination memory. So there is a long latency coming in, but there is not a long latency coming out. So we don't need a very large buffer inside the DMA, as we can use as, we can transfer directly into the destination memory the data without having to buffer it, which actually makes the DMA engine almost completely logic to handle the multiple outstanding transactions to the external interconnect, and doesn't need internal buffering. So this DMA channel is actually very small, and much smaller than a RDMA or a classical PCI Express DMA that you would have in a large computing system, because of no need for buffering. It is actually, but it's nevertheless a tricky control logic, because it has to handle all the slicing of the transactions and the multiple outstanding transactions and all the delivery issues that can come when you access an external interconnect, such as out of order and things like that. So it is a tricky piece of logic, but it is small. And this is a good news, because it means it doesn't add a lot to the area of the cluster. So it doesn't violate the efficiency. Efficiency is that most of the area of the cluster should be memory and processors. Okay, now what you need for making a good computer, a good parallel computer? You need parallel access to memories that we solved. You need the capability to manage the transfer to your local memories, which we solved. But you also need synchronization and atomics, because if you parallelize workload, sooner or later you have to synchronize. And if you share data, you may have, if you have multiple writers to the same data, you may have to implement atomicity. So how do we implement synchronization? How do you support atomicity? You need some dedicated hardware, especially for what concerns synchronization. So let me just remind you what the synchronization is. You spread work over the various cores, and then what you want to do is that the core go ahead independently and do their work, but when this work is over, they have to wait for each other before they move to the next part of the work. This is a so-called rendezvous or synchronization point. How can you implement it? There is an easy way to implement a synchronization using atomics and critical sections. But atomics and critical sections have several shortcomings. One of the shortcomings that we want to address here is impacting energy a lot. And what is the problem? The problem is that if a processor is, if we implement atomicity, if we implement synchronization using atomicity, then a processor that goes to an atomic variable for synchronization and finds it's locked because another process is accessing it, it has to try again. So this retry is an energy expensive because it is a memory transaction that has to be done multiple times until you find your lock available. Especially if you have very small synchronization regions, then you will have a lot of traffic into the memory because of these multiple atomic accesses. How can you address this problem and how you can make it more energy efficient? Well, the idea is actually very simple. We want to avoid busy waiting, and we want actually to put the cores that are waiting on a barrier, on a synchronization barrier, we want to put them to sleep and only wake them up when the barrier is reached by all the cores. So we implement this using a specialized synchronization unit, which is fast and extremely energy efficient. What is the concept here? The concept is that whenever a core has finished, it will send a signal to the synchronization unit and it will put itself to sleep. Then the synchronization unit will count all the signals as shown here into the animation. Sorry, let me bring back the animation. So, you know, first signal, second signal, third signal, and the fact that it disappears means that they sleep. And then when the final 4 signals have achieved, the counting semaphore or the counter into the synchronization unit has reached the count of 4, which basically means all the cores have reached the barrier, then it will activate them using an event as soon as the last one has arrived. So this block has been implemented with dedicated hardware, which manages this, quiet synchronization, non-polling synchronization, and removes all the needless or the useless switching activity related to polling synchronization variables. So without going too much into details, the access to this synchronizer is implemented with a very small piece of software that essentially signals a memory mapped variable when the processor ends its parallel region, and this is done with a memory mapped instruction, so a memory mapped access, so one load, and then the core goes into wait for event. And so it means that the core clock gates, doesn't burn any more power, and will be waken up by the specific event that is the end of, that is triggered by the unit when all the cores in the barrier have reached the synchronization. So the protocol is here. I don't want to waste your time with details, but I just want to show you that as soon as the read the request, remember the request, the synchronization is implemented as a memory access. As soon as the read request is implemented, the core stops, and immediately after the event arrives, the core starts again. And you can see here that the clock is stopped while the event is being waited for. So it's a very simple API. it is super fast to implement, to run, because it needs just a couple of cycles to make sure that the pipeline has completed its execution, and then the core stops burning energy, and it will restart only when the barrier is reached. So is this important? Oh, yes, it is actually important. You can see from these plots that the compared to a test and set barrier that is using an atomic variable, the traditional way, even on the local memory, so the atomic access is very short, it's only a couple of cycles, but it has the problem of polling. So you see that not only the number of cycles is lower, but the energy is much better, especially when you start having several cores that synchronize, so they will pollute their own, and they will have a lot of weighting and a lot of contention for weighting. So you see almost almost 2 orders of magnitude improvement in energy efficiency. Is that does it matter? Well, at the application level, it actually matters a lot. This plot shows what happens in terms of parallel section size. So the amount of work that a core will have to do before synchronizing. So as the size goes up, synchronization is amortized, because if you run in parallel without having to synchronize for 1 million of instructions or 10 millions of instructions, then even if you lose a few hundred cycles or 1,000 cycles for synchronization, you don't care, because it's percentually small. But since we are working on small memories, we cannot assume that we will have millions of cycles before resynchronizing. Our workload has to be frequently synchronized. So we need to be in a region where we can afford to also run very small parallel regions without a lot of overhead. And as you can see, when we use our SCU barriers, which are the blue lines here, we can afford, without impacting the execution time by more than 10%, so very low overhead from synchronization, even if our sections, parallel sections, are in the order of 100 cycles. So to remember, with this specialized hardware, we can run parallel section of a few hundred cycles, maybe couple of hundred cycles, with a negligible synchronization overhead. This is not the case when you use a test and set, where you need the parallel section of at least 1 order of magnitude larger number of instructions. Okay, so we solved another problem. The problem here is to be able to run effective parallel software, which needs synchronization in even very small parallel sections without a lot of overhead. So all the tricks that I explained here I'm also showing critical sections, but let me skip these details. So all that we have described here is actually allowing us to implement the parallel execution in an efficient way. So the idea here is that there is one of the cores will manage the DMA transfers. The DMA transfer will copy the new data into the cluster, while the processors are working on the previous frame of data, and the event unit will synchronize the cores whenever needed. So the cores will work on the data that has been copied by the DMA in the previous iteration, and the DMA will use the remaining part of the memory to copy the new data in parallel while the cores are working. And the event unit, together with the synchronizer, will manage the synchronization of the cores among themselves and the cores with the DMA in a very efficient way. So during execution, you have all the cores working in parallel in the memory, the DMA doing the copy in parallel, and everything is orchestrated without conflicts and without memory overrides by the synchronization units at very low overhead. So the last point that I want to stress, that I so far glossed over, is what about instructions? Because these are processors, they are not an accelerator. So this processor fetch instructions. And now we have made a problem for us. What is the problem? The problem is that before we have only one stream of instructions that has to be fetched by the core. So no problem. But now, as we increase the core, we have more and more streams of instructions that have to be fetched by the cores. And this is actually overhead. Well, each core will have to fetch a stream of instructions, and then, you know, if they all go to a global memory to get the instructions, you will lose all your energy efficiency because of this huge instruction bandwidth that you have to provide from the memory to the many cores. And all the cores always fetch instructions every clock cycle. So the traffic to that instruction memory is enormous. How can you do that? You could replicate the instruction memories, but that will have a very large cost. Otherwise, you can implement an instruction cache. So here, the concept that I show here is that you have a private instruction cache for, but you know, you may already start thinking, well, you know, instruction cache is expensive. You already told us the cache is expensive, and here you want to replicate the instruction cache all over. It's gonna cost a lot, and you would be right. So what happens? How can we do this? Well, first of all, we need to really decrease the cost of accessing this memory, because this is the most dangerous memory to get, to have a high cost on. Why? Because this memory is accessed every cycle. You need an instruction every cycle. So, and also memories don't scale up down very well with power, so with the voltage. So you will need to have in the instruction memories, you will need to have efficient memories that have a very low energy cost, and they scale down in voltage very well. Otherwise, when you go to near threshold, most of your power will be in fetching data from instruction memory, fetching instruction from instruction memories. Actually, the most efficient memory they can implement today is using standard cells, using latches in terms of energy efficiency. Why? Because latches can be scaled down in voltage exactly as logic, and not as SRAM, which stops scaling down in voltage much earlier than logic. So let's implement instruction memory with latches. And the reason why we want to use latches is less energy per access, and also scalability in terms of voltage. But you immediately think about density. What about density? Well, latches have a much worse density than SRAM. So you have a problem. You have much better efficiency in accessing the memory with instructions, but with latches, but your SRAM density is compromised, and you have to pay a lot of area for this latch-based memory. So how can you solve the problem? Well, again, architecture comes to the help here. So the idea is that we want to implement cache that has a size of a few kilobytes, and have each core have the view of having a few kilobyte cache, implement this cache with latches for maximum energy efficiency, and not pay a lot of area for it. The reason why I said a few kilobytes is that most applications that have this tight kernels like machine learning and loops and so on, they spend a lot of time in an inner loop, and most of these inner loops will fit into a few kilobytes of cache. So ideally, a few kilobytes of private cache made with latches would solve the problem. Unfortunately, the problem is that a few kilobytes of cache per processor made with latches use a lot of area. So how can we fix the problem? Well, we fix the problem with architectural tricks. And the idea here is that you develop a hierarchical instruction level cache that is actually using only private level 0 cache. That is, if you want, a loop buffer that is very small, implemented with latches, and super energy efficient. Then you have an interconnect, like the one that we use for the data memory, that multiplexes the misses into the L0 cache into a multi-banked cache, multi-bank memory that is containing instructions, a larger set of instructions. However, this size here has not to be as large as replicating the cache for all the processors. The reason is that in most of the cases, we are actually running the same code for all the processors. Remember that we are running, in a sense, a SIMD type of code. It's a loop where the same iterations are spread over several processors. So it's a for loop where one iteration, 50 iterations are on a single processor, other 50 iterations are on the same, on another processor. So in this type of parallel loops, the code base is the same, and so you don't really need to replicate. So we have here a shared cache, a shared memory, where the single piece of code that all the cores are executing is stored, and this piece of data is broadcasted through the logarithmic interconnect. This piece of instruction is broadcasted to the logarithmic interconnect into L0 buffers that decrease the likelihood of having banking conflict into this multi-banked share instruction memory. So this is what we call hierarchical shared cache. That is what we implemented in our course. Now, the advantage of this cache is that you get better performance than a private iCache, and the reason is that private iCache will have to be much smaller. So in the private iCache, you run into capacity problems, and better energy efficiency than a purely shared cache, because of the fact that many access to the shared memory banks are filtered by the L0 buffers. So as you can see, this is an architectural design problem targeting this specific energy efficiency requirement of these guys. So the results are that we can effectively parallelize the parallel applications that we have, like the machine learning cores, and this actually shows that from one core to basic baseline garden variety RISC-V to our RISC-V core, we have almost one order of magnitude speed up on sequential execution. And then if we move from one core to 8 cores with the machine learning workload, this is a real workload, we have almost linear speed up. In fact, at the end, we get 7.5x speed up over 8 cores. It means that this 0.5 loss with respect to ideal speed up is what remains as architectural effect of all these non-ideal multi-ported memories that we have. So sometimes we have memory conflicts, sometimes you have to wait, but the wait is actually fairly small, and it's only hitting you by half a processor over 8 processors. So, which means that we can very effectively parallelize our workload without losing a lot of energy. So, this is the key idea of parallel ultra-low power. Now, if we scale up at the system level, we also have the fact that in many cases our workloads don't need all these computing capabilities that we have. And many cases, your workload is just waiting for some events to happen and has to manage like control facts like, waking up, waiting for events, managing the peripherals, and so on. So we need an heterogeneous architecture. So we need actually a subsystem that is managing our chip when there is not so much to do. So the cluster will be power managed, will be in shutdown, and this block here, it's a normal single core microcontroller that manages the time where you don't have a lot to do and you have to wait most of the times. You still need memory, you have all your IOs into this domain, and you have also the external memory access in the domain. So this is your, let's say, input-output frame, and the cores will be turned on and activated on demand when you have a lot of work to do. Now, one challenge that you have in this subsystem here is to manage effectively these IOs. Now, the IO subsystem is, needs quite a lot of control workload. For example, managing the input-output protocol for the data that comes in. So we decided to actually design an autonomous memory IO system. This autonomous memory IO system is called the microDMA, and fundamentally has the goal of managing the peripherals and managing autonomously peripherals and actually implementing memory transfers from the peripherals directly to the on-chip memory without with minimal intervention from the input-output core that we have into the SoC domain that is not a cluster. Now, we realize also that instead of just managing the input-out protocols and the data transfer into the memory without the intervention of the core, this DMA engine could also perform some simple computation. Let me give you an example. For example, if you want to do a simple FIR filter on the data that comes in from your analog to digital conversion, you may transfer a block of data, then wake up the processor, then get the filter done, and then go to sleep with the processor. Or you may actually have a small DSP filter that just does a FIR filter on the data that streams in without waking up the processor. So our micro DMA is not only able to manage autonomously the peripherals, the sequence of the signals on the peripherals, but also to perform some simple and local computation on the stream of data that is coming in and put it into memory already filtered. So the effect of this capability is that you can trigger your core to manage the input-output much more rarely than what would be needed without the micro DMA. So your input-output core stays in sleep for a very long time, while the micro DMA creates frames in memory that can then be processed in larger blocks by the processor or by the cluster, and the power consumption of the micro DMA is much lower than the processor working on it. So we improve the energy efficiency thanks to this. Also, we need to manage interrupts because all the units, I/O units, typically provide interrupts. So we also need, of course, interrupt management. This is quite a standard capability that you must have in your SoC, and we, of course, we design, but I won't spend a lot of time on it. Yeah, I want to spend the last few minutes of the lecture just to describe the last key functionality, which is what if we wanted to actually have some sort of hardware-specific acceleration in our cluster. So what if our cores are not efficient enough? For example, if we have to do a lot of multiply accumulate operations, the cores can do very well multiply accumulate operations, but they of course have to fetch instructions and to decode instruction for doing that. If we have a huge number of multiply accumulate operations, we may want to have an accelerator that is specialized for that. So we define the concept of hardware compute engine. The hardware compute engine is a specialized engine that does not need to fetch instructions because it's specialized, and accesses the shared memory like the processors. At the same time, it doesn't need to fetch instructions and doesn't need to pay the von Neumann bottleneck of the processors. So the key idea here is that this hardware accelerator will be sharing the memory, the TCDM, with the cores, so we don't need to have copies of data from the accelerator to the cores, but they will share the memory. So this hardware processing engine is made as from the control plane is a peripheral. So the processors will program this unit by telling the unit what to do through control ports using registers that configure the unit. And then, from the point of view of the data on the data plane, the accelerator will look like a few processors, because if the processor has the accelerator a 4-port into the memory system, it will generate traffic like 4 processors. So from the control plane, it looks like a peripheral. From the data plane, it looks like a set of processors. And then internally, you can have your dedicated data path that makes all the data processing specialized that you need. And of course, you need a bit of a plug into the memory system, because this internal logic may not know about addresses in the shared memory. So you need address generation logic to be able to get your data externally from the shared tightly coupled data memory that the accelerator and the processor they share. So the processor, the hardware C is made of dedicated data path that is performing the specialized class of computation that you need. It has the memory interfaces for address generation, so to be able to interface with the memory system, with the TCDM through the interconnect. And it also has a target port with control registers that are used to program the functional units that you have inside. This is a very simple toy example where the dedicated data path is only doing multiply accumulate, which is not so useful, but is actually an example that we open source so that people can use this plug as a template to add their own internal logic. For lack of time, I will not describe a real hardware accelerator like the convolutional engine that we use in some of our implementations. So this part I will skip, but fundamentally this part has the same input-output of the toy hardware accelerator that I described, but of course much more complex internal functionality. It is a systolic array of multiply accumulate units that can perform 25 or 50, depending on how many units you put in the systolic array, multiply accumulate per cycle, so it could greatly accelerate convolutional networks. Let me skip the details of this and move toward my last slides. So the last element I want to give is that sometimes you also need some specific specialized hardware in the always-on SoC domain, so not within the cluster. This is, for example, if you need to trigger your system with some data that comes from outside. So, for example, if you are monitoring an accelerometer and you want to see if the accelerometer is passing the threshold, and this threshold will wake up all the system. So this threshold passing can be implemented with a single analog circuit, which is an operational amplifier. But of course, you may need something more, like what if you wanted to wake up the system if you have seen 3 crossing of a given threshold, or 4, and so on. So you may need some sort of a specialized wake-up processor that can be implemented in the always-on domain. So we call this a smart wake-up module. And this is fundamentally what I call a wake-up accelerator. It actually implements complex functions like multiple crossing detection or even classification of patterns, but directly on the input data. And its goal is not to provide a final classification output, but just wake up the more powerful and smarter processor that will perform the fine, detailed, and accurate classification. So just as an example, we have a very interesting, soon to be open sourced wake-up processor based on high-dimensional computing, which is directly getting the data from the peripherals, is performing classification, first-stage classification, and then is waking up the rest of the system when something interesting can be seen and has to be more carefully analyzed. Just to give you a feeling, this wake-up processor consumes only a handful of microwatts, so it can be always on and without exhausting the battery of your system, while if you turn on even only the basic single processor in the system that you see in the SoC, we have to be ready to spend hundreds of or tens or hundreds of milliwatts. So if you have in the hundreds of tens of milliwatts, single milliwatts, or hundreds of microwatts, so you have at least 1 to 2 orders of magnitude higher power if you have to perform data processing with the processor, or even more with the cluster. So to summarize, as you have seen, developing a fully functional open source hardware platform is not only making RISC-V cores. You have to make sure that these RISC-V cores have peripherals, interconnects, accelerator plugs, so that they can be assembled into useful system on chips, like a single core system on chip, multi-core heterogeneous system on chip, or many core system on chip, cover the spectrum between the ultra low power IoT and the high performance computing, very high energy efficient. So my last reflection is, maybe you wonder what is open source hardware after all this discussion. So let me close the lecture by giving you a clear definition of what open source hardware is. Is RISC-V an open source hardware? No. RISC-V, as Frank has explained, is not open source hardware. It is an open source ISA specification. So it's a document. It's a very nice document endorsed by more than 300 companies, but it is not open source hardware. It is, however, a prerequisite for open source hardware. If you don't have an open source ISA, you cannot make open source hardware based on this ISA. So, what is then open source hardware? Open source hardware is fundamentally RTL source code. So, System Verilog, VHDL, whatever. We use a System Verilog. This is similar to your C code, but so it can be open source because you type it in. It doesn't have any legacy IP that so you can release it as you would release your C code or your Java code. So this HDL code is what we call open source hardware, really. But is it sufficient to make open source chips? No. Open source hardware is only the entry point for a very large path that leads to silicon, and this is using proprietary tools like from EDA companies, proprietary information like the one that foundries will give you to make the silicon, and maybe also some proprietary IP that is needed for your chip to work, like a clock generator or something like that. So all this stuff is not open source, but open source hardware is a step to make an open source chip. Now, things are improving. You may have seen the announcement from FOSSI last week that, there is a flow that is all made of open source components across all this hardware stuff that is traditionally not open source. However, this flow is for a very simple technology, 130 nanometer technology. So if you want to do your system on chip in 22 nanometer technology, still you are stuck with a lot of closed source stuff. Nevertheless, what we call today open source hardware for pulp is the open source HDL description of all the IPs that I described in this presentation. It's liberally available, so with a very liberal license like Apache. Now, my last slide is nice concept. Is it, academic work? Is it only on paper or maybe on some FPGAs and so on? No, all this has been taped out multiple times. We have made of pulp 37 chips, and actually right now they are around 40, but some of them we cannot talk yet about it. And in the next and the last part of the slide of this lecture, Frank will talk about experiences in making these chips, and really experiences from the trenches and implementation experience, which is the last the last topic that we'll cover into this lecture. Thank you for your attention, and with that I'm done. And if there are some residual questions that Frank has not exhaustively answered, I can spend a few minutes to answer them.
Yeah, Luca, I left some for you because I know, well, one I don't know myself, the other one I know you would like to talk about, so.
Okay. So I see a few questions, 3 questions. So there is a question on the DMA. Is that DMA described right now exactly like store and forward? Well, in a sense, the idea is what you would have in some sort of wormhole network where you immediately start propagating your data in the next hop. So ideally, that's also possible for DMAs. You don't need a lot of buffering if you use this type of strategies. On the other hand, unfortunately, the picture is not so simple, because usually DMAs bridge information between 2 different protocols. So, for example, PCI Express on one side and AXI on the other side. So this protocol mismatch is what requires buffering. within the same protocol, you can actually do store and forward if your protocol allows it with the proper control flow. But most of the times, the DMA is actually bridging between two different protocols. So store and forward is not so simple in this context. So there are a couple of other questions. How are the neural network activation function other than ReLU, such as sigmoid, managed? Oh, that's an excellent question, actually. Thanks, Frank, for not answering to it. Actually, this is actually the real point for which we believe in this shared memory architecture. The reason is that, as you know, doing this nonlinear function like sigmoid or ReLU is not so computational intensive. So actually, if you look into it, 99% of your workload is convolutions. And if you have to add also the sigmoid computation capabilities or the ReLU computation capability in the hardware accelerator, yes, you could do it. It's not so complex. But you want to change the performance a lot, and will make your hardware accelerator very specific, in the sense that what if you want this hyperbolic tangent instead of ReLU. So the reason why we want to tightly couple processors with accelerators is that we want to put into the accelerator the computational intensive part that hopefully will not change, like sum of products. And we want to keep the processor free to actually do stuff that will probably change and it's not so computational intensive, like deciding what activation function to use. For example, ReLU or sigmoid. And in that case, the processors will be busy doing sigmoids, but since sigmoids are like 1% of the total workload, they will be still making it fast enough to balance the throughput of the accelerator. Okay, many of these architecture choices are made to support a specific kind of application, like a neural network. Well, actually, this is not true. I gave the neural network as an example, but the cluster engine is totally flexible. And this is actually what makes it very valuable and very general purpose, even more than GPUs. The reason why the cluster that we described here is really a parallel computer and not you know, a data parallel computer like a GPU is that, as you may have noticed, the cores don't have to perform the same instruction in the same cycle. They have a separate fetch logic. So in reality, the processor can possibly run different pieces of code or even be misaligned. And so there are no problems like branch divergence or things like that. So in a sense, this is a really parallel computing machine. So it's not specialized for neural networks. Of course, if you add an accelerator for neural networks, it will become specialized for neural networks. But from the point of view of the architecture, this is a really parallel machine. It's not a dedicated hardware for neural networks. Yes, of course, we tried. You can see in the papers, there are plenty of papers where with this target, this accelerator is targeting, you know, generic DSP that goes from SVM to FFT to you know, transforms of various types to you know, dimensionality reduction algorithms, hyperdimensional computing, binary caching function, and things like that. So indeed, it is really flexible, and I think this is one of the distinctive features of our pulp approach, and the reason why we use a RISC-V cores is exactly that we want to have a full flexibility and not to design a specialized engine like a systolic array that will do very well on a neural network, but will do nothing about, for example, you know, PCA. You know, PCA is a very useful algorithm for dimensionality reduction, and the systolic arrays have nothing to do with PCA.
Yeah, Luca, maybe when you look at the answered questions, there were a couple of things coming about the cluster operations, whether or not, you know, there are multiple threads and caches and things. Maybe if you can say a few words about how we generally use them, not like a general purpose Linux-like operation.
Yeah, I mean, the important point about this cluster is that it is not definitely a general purpose Linux-based system. What is missing there? For example, it does not support virtualization. So it's only working in physical memory, and the processors are meant to work in essentially at high efficiency. They will work into the TCDM interconnect, in TCDM memory. Second, the TCDM is not a data cache. So if you are, for example, plan to use this cluster to browse a very large data structure that with a random access pattern that sit in main memory, in external memory, then you will not get any energy efficiency. So this is actually the restriction in application domain of this cluster, is that it has to handle data that can be efficiently double buffered. So if you if your data is organized in chunks that can be efficiently double buffered, so where you can have the DMABs copy the data in, and then your compute engine working on one frame while the next frame is being copied in, then in that case you achieve extremely high energy efficiency. If you want to use this as a general purpose compute engine that has flat access to 4 GB of addressing space, then you will not get any energy efficiency, because most of the times the cores will be waiting. The core can access external memory, but will take a lot of cycles, and since they don't have a cache, they will wait for a long time. So it works very well in application that can be transformed or formulated with this type of double buffering data frame. Can an extension added to the RISC-V course to put in a mode to do multiply accumulate operation without fetching instruction? Yes, actually, excellent question. There are a lot of good questions here. So yes, and in fact, what we do is exactly that, but we do it in a more general way. Fundamentally, we use the loop. We support the hardware loops. So whenever you are in a hardware loop, you don't fetch instructions fundamentally. You keep your instructions from L0 buffer, and you have your data over there, and so you will not exit this loop for a long time. Now, you may even be more aggressive and you may even want to completely stop the decoding of instructions and even the fetching from the L0 buffer to save further memory. And we actually do that in the new generation of processors. These are the processors where we're actually using the so-called FREP and SSR, the so-called snitch processors. You can find information about the snitch processors online. We have several papers published on archive, but we don't cover them in this presentation because they are more advanced materials that are not covered here. So it's an excellent question and actually a very good point.
Yeah, I pasted the papers to the question. I think it should be visible.
Okay. So the present emulated multiport memory works as long as words are accessed one by one through, if through a caching mechanism, consecutive addresses are fetched simultaneously, the benefit of the interconnect will be lost. Not actually. If consecutive addresses, if you have one processor accessing word n, another processor accessing word n plus 1, it's actually the case where this interleaving scheme shines, because this is the case where since two consecutive addresses are stored in two different banks, two processors can access concurrently consecutive addresses without any problems. Actually, where we see most access contention is when you have some adverse patterns where the two processors access data in a modulo fashion. So processor number 1 access the data at address n, and processor number 2 access data at address n plus 8. if you have 8 memory banks. In this case, the two processors will always have contention. However, this type of pattern is possible, yes, but it can be and is pathological. It can be avoided by slightly shifting the execution time of the processor. So if you dephase the processor by 1 cycle, which is actually very easy because the first time they have a conflict, one of the two will wait and the second one will go ahead. So from the next time over, they will be misaligned. So overall, the processors tend to misalign themselves because of the waiting caused by the banking conflict that they have, and the banking factor is quite efficient. Now, if you make your processor super efficient and the processor do, all of them access the memory all the cycles, then you will have a higher banking conflicts. In that case, there are some other tricks that you can play, like, for example, having multicast in the memory system or increasing the banking factor. Ultimately, there will be a memory bottleneck if your cores are accessing the data all the time. And we see that in the most modern version of the RISC-V, the RISC-V cores that we have not presented today, which has a superscalar capability, fundamentally is capable of, even though it's not implemented as superscalar, is capable of doing MAC together with a load in the same cycle. In that case, you have potentially loads in all the cycles, and you may have larger banking conflicts. Without this core, we never see banking conflicts for more than 10% of the cycles. With this new core, we can go to 20 or 30% banking conflicts. And then in that case, there are some extra tricks that you can manage, like having some special buffers for local memories, or having some misalignment of addresses. But these are more advanced tricks that don't have time to cover here.
Okay, I think, Luca, you are checking the answered ones. There are also a couple of open ones. But if you want, let me start presenting slowly.
Yeah, I can also answer a few open here. Have you tried another workload CNN, not CNN, like I answered? Would the architecture change drastically? I think I answered to that.
That's the answer tab, actually. There is the open tab.
Open. Oh, I see. Open. Okay, sorry. Has been any need felt to add special instruction for TANAC? Yes, of course. This is actually published. This is a special instructions supported. This is actually published in this year date. DAC, sorry, has been is going to be presented this year, but you already find it on archive. So we did add instructions using with the capability of perform arctangent and all the needed for sigmoid. Is a CABA simulation of the architecture? CABA stands for cycle accurate, I guess. Anyway, so yes, we do have a virtual platform. It's called, and this virtual platform is also available open source. And yes, and it's also not cycle accurate, but it's timing accurate in the sense that it gives you timing estimates around 10%, 10-15% from the actual hardware. So yes, and it's open source, so you can modify it, work on it, and try stuff. What is the clock frequency when operating a near threshold? Is there a variability related? Oh, that's actually another good question related to implementation. I think that one Frank can address because he will talk about implementation. So since I also have to stop because otherwise we run out of time. And maybe last question. Are you aiming at some specific type of embedded system with this course? That's a good question. So if you want like a marketing response, please check the website of Greenwaves Technology. Greenwave Technologies. This is a company that is actually using our open source IPs to build the so-called IoT processor. So an IoT processor is essentially a microcontroller on steroids. It's a microcontroller for simple control operation with the cluster of these processors to perform heavy data processing, machine learning, audio processing, and all these type of things. So You will see plenty of application and marketing material from that company if you want to see more a marketing aspect. Otherwise, at the end of Frank's lecture, there are a few pointers to papers that describe applications of clusters of pulp in various domains that go from security to IoT to machine learning, of course, and other stuff. How does pulp can communicate with the cloud? Last question, then I'll have to stop. Actually, that's a nice question. The communication with the external world can be managed as a normal microcontroller. So the microcontroller that you see on the left-hand side in my diagrams can actually manage the communication stack, and then connect to or even embed on the same silicon all the baseband processing. Now, it's not completely public, but there are a couple of companies that are already implementing their transceivers using our pulp cores. For example, one of these companies that is using our pulp cores for implementing IoT and BIoT transceivers is ACP, Advanced Circuit Pursuit, which is a Swiss company that is developing, among other things, NB-IoT modems and things like that.
Okay, so I think I can take over. So this is the last part, and we thought it would be interesting to talk about, we know now the basics behind it, what we want to achieve, but how does it go from concept to reality? So I will have basically three different parts. First, I will talk about single core microcontrollers. Then we will talk about the many core systems that Luca was describing in this morning. And then I will have also a chip that has accelerators and it's a more advanced system. And lastly, we have also the good, the bad, and the ugly, just lessons learned. Also, we will show that it doesn't always go very, very well. We also make mistakes. So also to briefly talk about that. So we will briefly talk why make chips at all, the use cases, why we do it. Then, as I said, there are in the parentheses, the chips. We have 37 chips that that came back, that we manufactured. Luca was talking about until the end of the year, we have 3 more going out. So there's plenty of them. There's plenty of things we tried and examined. And these are the names that we are looking at that. First of all, this is a question that comes a lot. We are a research institute, it's both University of Bologna and ETH Zurich. We are universities, we do research, we do not have manufacturing of large scale. So what we do is we take advantage of systems called MPW, multi-project wafers. And this is a service that is provided also to the industry to share the cost of manufacturing. So a large cost of manufacturing ICs is an upfront cost you have to pay to make the masks that is the building the way it is being manufactured. You need a number of lithographic masks, and they sum up for modern technologies to millions of dollars upfront costs. You have to pay this, and then if you have a large production, your cost will go down because the unit cost is very low, but the upfront cost is high. So what do you do when you want to just test something? If you have an idea, you cannot afford to have a full production. So what is being done is usually many people, independent people, join and share the cost of making the masks. This is called the MPW service. There are actually services like Europractice IC, which has been very, very helpful for us. And I've stolen the picture from their website that explains this. Reserved area, so this is the reticle. This is the repeat pattern that goes onto the wafer. And that one is shared among 10, 20 designs. And each one of them contributes to the cost of the upfront cost in accordance to their area. And they announce some dates when these are available, you register for them, you pay the price. So just to give you an example, if the mask costs 1.5 million, if there are 10 projects, each one of them will be paying 150,000 per project, and but you are also not getting a large production out of it. So what happens is only a few wafers are produced this way. Usually, I mean, the number varies, is you get 50 to 200 chips. If you think about it, for those few chips, you're actually paying a very high price. So the most we paid is 150K actually for only a portion of this thing in 22 nanometers. And there are some older technologies where doing this is possible for a few $1,000s. So if you're doing it in 350, 250, 180 nanometers, the costs are not that high. If you want to go to even smaller technologies, even the MPV costs are very high. But you have to realize that all the chips we are talking about are done through MPWs. We have at most 200 of those chips manufactured. This is enough for our purposes. What are we doing? What are our purposes? A couple of the chips we design are from beginning very clear that they will land on an IC tester. So you see here, this is a complicated device, cost a few $1 million. You plug your chip in an environment that is able to send data, receive data, measure performance, change the frequency, temperature, and everything associated with the chip that allows you to make a characterization and understand how the chip works, what is its performance. And this is one of our main works. So roughly half of our chips are taught for testing on such a tester to be characterized to understand what is happening. And then there are some chips. So here you see this is the chip that we will also talk about. This is Mr. Wolf. It gets then, it graduates from being a tester-only chip. It has to have real interfaces. It can communicate. It can, besides working well, it can also communicate with its environment and work reasonably well so that it can be integrated into research prototypes and demonstrators. So this is, I'll talk about this project in a little while. And what also happens is, this was a very nice surprise for us. The chip that you see here is actually manufactured by NXP, OpenISA org, under the OpenISA org name. The board is called Vega. It's a development board where they actually independently from our open source repositories downloaded the core. So there's a RISC-V core and a zero RISC-V core inside. And they were able to manufacture and do this for themselves. So it's not us, it's someone else actually makes real working silicon out of the things that we have made. And this was really one of the happier things I've seen as part of this project. Out of the blue, NXP sends us a box and says, here, it works. We made a chip out of your things. So all our development, most of what we show is openly available, and all our development is on GitHub. So this is the link to our GitHub repository. And as Luca was also mentioning, we are using a permissive license that allows anyone to use, change, and make products without restrictions. In the meantime, this is an older screenshot. You realize, for example, the Ariane is now being hosted by Open Hardware. Similarly, the RISC-V is also being hosted. That's the RISC-V processor. It is also being hosted at Open Hardware Group, which is nice. So we have released a large number of IPs. That's what we were talking about. So these are not only the cores, but you need also a lot of things around to make the platforms, multi-core systems, and even multi-cluster systems available. So we mainly discussed about these cores yesterday. Today, we saw that they also come together, and our main activity was actually on the multi-core system. I'm briefly going to also start with the single core systems because it's an easier progression. And so let's get started. If you've been following what we were doing, Palpino is our first open source release. It was released early in 2016, and it was a simple design. It was, we were also trying to figure out what it means to do an open source release, what kind of things you have to think about. And this is a core. At the time, it was a simple RISC-V core. And we didn't want to, sorry, I need to make some space on my own screen because I don't see that part. We we didn't have the time to think about it more. So we have a separate data memory and a separate instruction memory attached in the chip. Why? Because it was the fastest way to do it. We were not trying to advocate to use a Harvard type architecture, but making sure that there is an interconnection between the memory that allows the processor to at the same time access data and instruction was more work. So we ended up copying the available IOs, IPs, and interconnects into it, and made a small and compact release. And this is a good lesson actually for everyone else who's interested in open hardware and open source releases. This thing is, when we talk about people, Palpino comes up all the time. Everybody talks about this. It is not really that much of something that is special. You will see what we are actually working on. What we find more interesting are the more complex architectures, but we didn't have time or we weren't ready to release them. So we made a quick release. And this release has attracted most of the attention. And we are still, answering a lot of questions about Palpino. It still works. It's good if you are making, if you're just interested about the core itself, if you want to test the core in a nice environment you want to see. Okay, but what about the chip? So this is Imperium, designed by Florian, who took a RISC-V core, added 64 kilobytes of memory. It has basic peripherals. The chip has only 40 pins, so it doesn't have that much of interfaces. And the chip actually works up to 500 megahertz in a 65 nanometer technology. And the main challenge, for example, here was to find fast memory cuts so that it would work at that speed. 500 megahertz means that your critical path is 2 nanoseconds, and a significant portion of that time in this technology is taken up by the memory read and the memory access time. So in this one where Florian wanted to go for speed. He went all broke for speed. So, instead of using a more compact and large memory, which would have allowed us to put more memory, we used 16 cuts, all of them smaller, to make this processor run as fast as possible. So this was the first trial, but it actually also ended up on a real design. So this is an Arduino compatible board. You see the chip here. You can also maybe make out that there is like text on it. So this is the third chip which we tested. It still has its markings on it. And you can also see on the PCB, this is a test socket. So we weren't even sure whether or not we need to use a normal test socket or can directly solder on it. And it was functional. It was even working. You could run programs in it. You see the USB connector there to access the processor, and it was a great success. But when you are talking about single core systems, I just want to talk about this particular chip. It's called Arnold. You see his picture there. This was a gorgeous collaboration. It was really one that I'm very proud of. The chip was manufactured in 22 nanometers. It's a RISC-V microcontroller system, so it's a single core system, but it's based around Palpissimo, the one that we would consider more advanced. And it joins an eFPGA, an embedded FPGA made by QuickLogic into one chip. And what I really like about this collaboration is the following. We met with the CEO and marketing officer of QuickLogic by chance in a Global Foundries technical conference. Basically, we were late for lunch and waiting in the queue, and we started talking. And it took us only 1 year to tape out this chip. And this is only possible because of the open source nature of what we had, because that allowed us to move in quickly. And recently, only 2 weeks ago, QuickLogic has made more of an offer to go open source. They announced in June 2020 that QuickLogic Open Reconfigurable Computing. And you can trace back all these things to a chance meeting going on and companies changing their ideas. So if you look inside it, this is now the Palpissimo system. You will realize a lot of the similar things that Luca was describing earlier. So we have the tightly coupled data memory interconnect. There is one core, it's not a cluster, there are not multiple processors there. It has a peripheral interconnect to do configuration and other things. The micro DMA that Luca was also talking about that allows to copy data in and out from peripherals to the memory directly is also integrated in there. And in addition, we have the eFPGA, which is here as an accelerator. It needs an adapter because the operating speed of the eFPGA in this case was around 120 megahertz, whereas the RISC-V part works at 400. And so you need to have a buffering so that you can talk with the same logarithmic interconnect over the memory banks. There were some additional memory and MAC units added to it, but this is essentially the thing. And it was an easy plug and play for us. So the remaining anything apart from this part was already ready, was already taped out, and we could drop in this thing as an accelerator into there. We are configuring, we can reprogram the FPGA over the APB port. And the nice thing, once again, is both the eFPGA and the RISC-V core are operating or are able to access the same memories. So sharing data or between them is very easy. So it can work as an accelerator for the core. At the same time, it can be also used, which is very interesting, as a configurable peripheral, meaning that it can access the I/O pins here, the GPIO pins directly, and adapt to existing to any protocol that you may find in the wild when you want to attach it to your microcontroller. Or it can be an accelerator for the I/O while the DMA is copying from the inputs or to the outputs to the memory. It can move them through the eFPGA and perform various operations like scaling, filtering, or generating histograms, which can then later be used for accelerating the process that the processor normally has to do. So this shows, for example, how the things that we were developing on our own then help us to join together, because if we didn't have this infrastructure and these solutions, once we meet with the people, realize what their block can do, joining them wouldn't have been so easily possible. So 1 year to go from meeting to a chip is, for me, a very nice achievement. Here there are you will find there is also the paper on the slides. Here are some numbers just as it is used. We had the IO subsystem acceleration. So in this case, the idea is that there is data coming over from the peripherals, and the eFPGA is doing some processing on it that works at 6 milliwatt. Compared to doing it only in the processor, that's an acceleration of 2.5. It can be a custom IO interface. So when you have a new system, new chip that you need to interface and you realize it is not fitting your existing SPIs, I2Cs, whatever. And in this case, instead of using the processor as beat banging over the GPIOs, we had 12.5 milliwatt in total. That's a 2.2x improvement. And we can obviously also use it as an accelerator working on the shared memory. There we could get, for CRC application, for example, we could get 42x of improvement. And there are many, many more ideas, because while running, you can even reconfigure the eFPGA. So it's actually a very interesting toy for us. And we were very happy or very proud to see that, hey, we have now so many more opportunities, and most of it is due to the way that we have configured things and have an open approach to it. If this was a proprietary system that we were developing, just setting up all these discussions and, you know, who owns what, how do we collaborate, would have stopped the progress here. And here you see Davide Schiavone, who was the lead on this thing with the test board for Arnold. So these things actually do exist and work. Luca talked about this at length. So many cores running at low VDD is more efficient. So we've already seen this. So it's better to have 4 cores running at lower voltage than 1 core running at nominal voltage. So how do we take advantage of this? We built these mini core systems. So the idea, instead of using a single fast core, we put them in a cluster, we share the memories, and we have maybe a hierarchy where the larger memory is outside. We use a DMA to copy the data into the local memory. There are no caches involved here. And maybe have a subsystem that also provides some I/O, so the system can also communicate with the outside world. So this is the most basic one that we were talking about. Notice that there is nothing more intelligent here. And this is exactly what our first mini core RISC-V chip was. We called it Honey Bunny. A lot of our chips have names from the movie Pulp Fiction. We like it. And it gives us a, when you have so many chips, you have to give them good names. If you're going Pulp version 1, version 2, version 3, you're going to run out of it pretty quickly. So this is our first mini core chip. I had the previous slides just to give this, give the connection to this. So this part of the chip has the cluster. It has 4 RISC-V cores. The drawing is not totally accurate. It's just to give you, it's not to scale. So the RISC-V cores are not as large and the memory is larger, etc. But just to give you an idea about how it is placed. It has 4 cores and 64 kilobytes of tightly coupled data memory in here, and as well as the DMA. And then what you have here is the SoC part, where you have the interconnect and the 256 kilobytes of L2 memory. And you run this at, or we were able to run this at 400 plus megahertz. At these speeds, it is not possible to, if you want this thing to run on a board, it's not really very practical to move this, the clock from an external source. You want to have something internally generated. And for this, we have designed our own frequency locked loop. It's not phase locked loop, it's just frequency locked loop. And so this was a new technology for us. Our previous chips were in 65 nanometers or in another technology. And the FLL we had was not adapted to this technology. So we needed to port the clock generator. Now, this design has analog parts. Because it has analog parts, it has layouts, we cannot make it available as open source. So this is also part of what Luca was talking about. So this is an IP, if you want. It's a hard macro that we had to generate and has plenty of restrictions, both from the PDK or from the tools needed to create it. And what is worse, for every new technology, we have to remake this. And in the meantime, we made more than 8 ports of it. And every time we have a new technology, this is some major effort that is needed so that you adopt these things. And if you are adding more things to your thing, if you are adding ADCs, if you're adding serial IOs, fast LVDS pads, etc., you also need to port these things. And you pretty soon realize, or you will see where the limits are. In our cases, the memory controllers for modern technologies like DDR or HBM are actually the major pieces missing for us to go forward and make even larger and more, let's say, capable chips. Just to show you that it works. So this is the famous visiting cards made by Stefan. And this is a working card. This is Honey Bunny. Once again, you see the number there. So this is chip number 15 that was tested. We actually have only 20 of them packaged on this flexible PCB board. You see that it's actually exactly the same size as a visiting card that we have. So it's this Honey Bunny there. If you turn it around, you can see that there is one battery that is needed to operate it. There are the power controllers. There is a JTAG interface, a power switch, and these are the SPI interfaces that are not soldered. If you like this sort of things, there is a video of how the board is assembled under this link here below. It was a fun exercise. And no, we don't have all of those cards. I think we have 2 assembled. And the rest of the visiting cards, some of you might have gotten from us over time, are just the board without the pieces. So the previous one, Honey Bunny, was a chip that had everything working. We had the clusters, but it didn't have too much capabilities to the outside. It also didn't have this independent part, the processor on the controlling part that could do more. So this one now is Mr. Wolf, is one of our more successful designs, and this one is the proper IoT processor, I would say. It was manufactured in TSMC 40. It is an 8+1 core IoT processor. So it has one cluster with 8 RISC-V cores. They also have an FPU unit, but instead of every core having a large fat FPU, they 4 cores share one FPU. It still has 64 kilobytes of TCDM memory. And then outside, you have the controller part, which has 512 kilobytes of RAM, all the peripherals, and an additional processor here to be able to work independently when the cluster is not in use. We will talk about the operating modes. You will see the controller and cluster at the bottom of the screen in a little while. And also what made this chip really interesting was we had on-chip voltage regulators. This is industrial IP contributed by Dolphin Integration, which was also possible because we were using an open source approach. So everything inside this chip is available as open source RTL code. That makes it attractive for companies also to collaborate with us and to share their things. So it is agreed that we could use these IP in this chip. Because whatever we do is also available to the customers later by Dolphin Integration. So there is a win-win situation for both parts. They get their IP, let's say, demonstrated in a much more interesting chip than a pure test chip. And we have things that we don't have a research interest in making it from people who know how to do it and use it. So this is just to show you how it looks inside. You can clearly see the larger memory banks. Here are the TCDM memories, and here you see the analog IP for the voltage converters. So the on-chip regulators now allow us different power modes. At the bottom, I have still the controller and the cluster. And in the best case, we are in the deep sleep mode, 0.8 volts, nothing is working. We have only leakage currents in 72 microwatts. And then you can also have a state retentive deep sleep. This means that the processor is not working, but we are powering the memories enough so that they can retain their contents. And so the power there is around 100 microwatts. The next mode is where you switch on the controller. So the controller is ready to work. It's clock gated. It's idle. It's not processing, but it's alive. So you can, the next clock cycle actually start working on it. It works in the range from 0.8 to 1.1 volts, and you are consuming something around 2 milliwatts. And what you can then do is, just run this as a simple microcontroller. There's a RISC-V processor in it, and it will run up to 450 megahertz, and at full speed, doing everything. It maybe has 40 milliwatts as its maximum consumption. So if the processing power of this is not enough, you can activate the cluster. So this is just cluster activated and clock gated. It's waiting idle. So you are consuming less than 5 milliwatts in this case. And then the cluster is active. There you have 8 FPU enabled RISC-V cores running up to 350 megahertz. And the maximum power you can get is 150 milliwatts. So this is the way it is working. It's actually a very interesting chip. And this release contains, it's the open pulp. If you go to our the GitHub page, so this is the code for that. It's a complex IoT processor. It's not like the much simpler Pulpino. However, when people talk about it, they will still mostly refer to Pulpino. I have to still say, and this is what Luca was also saying, there are many parts that we still cannot make open source. So there are technology specific information. There are all the memory macros, and we talked about it. The cuts that you select affect their performance. IO cells, any FLLs or analog macros, IO cells that we might have, we cannot make those open source. And you realize, for example, part of the interesting work here is the ability to turn on and off things. And this works very well if things are on chip. They don't work so well, or you somehow have to get an on-chip voltage regulator to be able to work with it. What this open pulp did, it facilitated a lot of interesting industry collaborations. Luca was already talking about green waves technologies, also Bitcraze and Dolphin. We ended up using it in multiple systems. We still build boards with it. I recently gave some to be assembled into boards, and we only have 200 manufactured. And you see various applications. So this is the drone version. So here it's in flight. Here it is in the early prototyping. We have one for measuring performance. We have one coupled with a TI ADC for measuring biosignals. And at the bottom, what you see is a commercial version of it. So once this was developed, GreenWaves Technologies made a version of it themselves. It's called GAP8. It is based mostly on OpenPulp. They have their own additions to it or their own omissions to it if you want. For example, GAP8 doesn't have an FPU. And once they saw what we were doing here, the drone underneath is being manufactured by Bitcraze. And they realized, oh, there is this good idea. They are making this nice application. So they actually, based on our open source releases, made even a product they are selling now called AI Deck. And in the meantime, GreenWaves is working towards the new GAP9 as a follow-up project. So just wanted to show how this Bitcraze thing came together. So this is the host drone. This is from Bitcraze. We made a shield to it that adds to this thing. And on top of the shield, the main part is the processor. We have versions with Mr. Wolf. We have this version is with GAP8. And this drone with only onboard computation is able to autonomously find its way. This is our corridor actually flying through there. And this entire thing, the entire board, not only the chip, consumes 64 milliwatts for running this application, which is actually quite amazing to see that it's possible. And this is only possible because of the way we have, of the way that Luca was explaining of working with the programmable system. And this is not a custom accelerator. It's not made only for this purpose. We can reprogram it and use it in a number of different ways as well. So I am moving now to more advanced nodes. I want to talk about one particular chips, the Cosmodrome. This was manufactured in GlobalFoundries 22FDX. In 2018, when we started working on it, it was the most advanced node available for us or for any university outside of universities that have direct collaborations with companies. The minimum size for manufacturing in this technology, MPW-wise, is 3 millimeters by 3 millimeters. And if you do the math and you look at it, I mean, that thing fits about 100 million transistors. It's a big thing. I mean, the designs that go in there to take advantage of it also need to fill up that area. The other nice thing about the FDX technology is it allows body biasing, which can change the behavior of the transistor after it's been manufactured to speed it up or to reduce its leakage. Now, with great power comes, as you know, great responsibility. So designs in 22FDX are more involved. There are more blocks, more functionality, which also means more things can go wrong. It's more challenging design, and such things are only possible because you collaborate with partners, in this case with GlobalFoundries, to help you also navigate through some of these difficulties. Also, you need to have ideas that could fill this chip. So if I'm putting a Palpino system into here, it would be on this one corner below one pad, and what do I do with the rest? So this is what's inside this first chip. So we have actually two Ariane 64-bit RISC-V cores. These are the cores that Luca was talking about yesterday. So one of them is here. The HP is the core optimized for high speed. The exact same core is also optimized using different libraries for a different operating point. We call it the ALP. There is the automatic body bias generator. So this is an IP contributed by Invecas, which was the foundry supplier for IPs in this particular technology. It allows the body bias to be tuned. In addition to that, we had some room. So we added our neural training accelerator, which has a lot of efficiency when you're working with training work. And the middle and the rest is actually common infrastructure. There's a large chunk of SRAM on this chip, so 1.25 megabytes. There's debug and IOs and other things. So just to come back to these fine-grained shared memory accelerators, this is the basic idea behind what we have in that accelerator. It is the same architecture that Luca was introducing in this morning. The one difference is instead of having many cores and one accelerator, there are actually here multiple accelerators and one core that does sort of kind of these bookkeeping, keeping those accelerators configured, as well as doing some rarely needed functions like the sigmoid, for example, and augmenting the functionality. So the concept is the same, it's maybe turned around on its head. And if you look into it, the NTX block has 8 such coprocessors, but there is still one RISC-V processor and the peripherals that work with it. And it also includes the 64 kilobyte TCDM in 32 banks and the logarithmic interconnect. I think there was a question about how much does it occupy in space or what are the areas. So here you see the sizes. This is a 22 nanometer as it was manufactured. And the reference is also available below. So this part runs up to 1.25 gigahertz, 20 gigaflops, a bandwidth of 5 gigabytes, and you can scale this up by replicating the cluster as many times as it is needed. The other part of Cosmodrome was the body biasing. So I just, for all the chips that I'm showing, I also want to show them how they worked, and I'll just now concentrate on the body biasing modes. We made this board for a demonstration for the global foundries. So this is the test socket inside where the chip is sitting. We have different powers, so the high performance core, low performance core, the NTX, the additional support. As you see, they have all separate power supplies. This is how we can measure them directly. In this case, because it's something carryable, we also had a USB attached small ADC board to do the sampling directly. We can generate the voltages here from one common voltage, so the supply voltages can be generated. The body bias voltage can be generated externally, and we have an STM microcontroller to do all the programming of these separate things. We have a USB connection to the computer to talk with everything else. So it's a great setup to show how things are working. I'll just introduce briefly 2 things. Not to run too much out of time. I think I'll finish in about 10-15 minutes if you can still hold on so long. So there are 2 things that we do with body biasing. The first thing is you will realize that when you manufacture chips, you have a wide parameter variation. So this is your typical case, this is your slow corner, this is your fast corner. And then the chips that you are manufacturing will fall into here. What you can do with body biasing is you can either make chips faster by forward body biasing, or you can make chips leak less by reverse body biasing. It's a technical discussion that probably I don't have time to explain all the details, but in this particular technology, you design, you choose whether or not you can do forward body biasing or reverse body biasing. You cannot do them at the same time. So it's either one or the other. In this case, what you can do is you realize that, hey, this should be my operating corner. You say, hey, chips should work at 730 megahertz at 0.65 volt and consume around 40 milliwatts. And then you pick your individual chip. For example, it lands somewhere here. In this case, it's working only at 490 megahertz, consumes 22 milliwatt. And by adding forward body biasing, you move it to the corner that you want. You can do this individually for each chip, effectively increasing the yield out of the selected performance target. The numbers actually correspond to the numbers that we're working on the chip. So this is the Ariane core working at 0.65 at 40 milliwatts, 730 megahertz. So in practice, you can get about 50% performance gain when you're looking at the operating speed with body biasing. Obviously, you are paying the price in power. So if you are working faster, it doesn't come for free, but it allows you a nice knob to play and to tighten your the parameter variation that you normally see in the manufacturing. The second one is gaining energy efficiency with body biasing. So in this case, we have a desired operating frequency, let's say around 800 or 850 megahertz. And we decreased the voltage, the supply voltage of the chip. So it was working at 0.8 volts. You decrease it down to 0.65. So this is the minimum level at which we are able to work. And then once we arrive there, we use forward body biasing to recover the performance that we lost. Because what happens when you reduce your supply voltage, the dynamic power consumption reduces by the square of the supply voltage, but so does also your operating speed. So you lose some of the performance. The chip that works at 850 megahertz at 0.8 volt only works at 490 megahertz at 0.65 volt. And then by applying forward body bias voltage, you can actually recover this performance back. So due to the dynamic, due to the increase in the clock frequency, you will be consuming a bit more dynamic power, but this is linear, whereas the reduction here was square. So in total, you have the same performance for 20% less power. So this is what we were able to demonstrate. So that was running on that board. The numbers actually correspond to the actual numbers that were running on that demo board. That is why you might ask, why do you look at 490 megahertz? Because that particular chip was working at 0.65 at that speed. So we get at least 20% more efficiency with body biasing in this case. Now, if you allow me a few more minutes, I'll just give you some of the experiences. We designed and tested a lot of chips, and you know, most work great. I'm actually surprised myself that so many of them work so great, but there were also mistakes made. And there's a look at what kind of things go right, and also talk about and be honest about what kind of things we make. So let's start with the good. Fulmine, this chip was actually, it's an earlier chip from 2015. It has 4 open RISC cores. They are not yet RISC-V. Before we switched to RISC-V, in the early days, we started in 2013. We were adapting, making our own versions of open RISC cores. But it's a similar system. It's a cluster-based system still. We have 64 kilobytes of TCDM, and we also have hardware accelerators already in it. There was one accelerator for side channel resistant cryptographic accelerators. This work was together with TU Graz, the group of Stefan Mangart, who is famous for his meltdown and spectre exploits, as well as a convolution engine, because somehow those things were needed. And we had a good publication which combines both things together by Francesco and the group of TU Graz. And we were extremely happy and proud to hear that this paper has been awarded the Darlington Award for Best Paper in 2020 by IEEE Circuits and Systems. It's great. I'm really speechless. It's actually even better because paper not related to this chip, but on our RISC-V cores, has also gotten the award for the transactions on circuits and on transactions on VLSI at the same time. So it was a major high for us. You should also notice how long it takes to reap the benefits. So the chip was from 2015. The paper is from 2017, and let's say the major recognition comes in 2020. So it also shows you that when you are dealing with actually manufacturing, measuring chips and doing this, there is a quite bit of lag until these things come out. So it's not like, hey, chip today, paper tomorrow, awards the next day. It takes a couple of years. So let's go to the bad. So yesterday, Luca was talking about this. This is Poseidon. It is our first 22 nanometer chip, even before the Cosmodrome. We use the Europractice IC service. I paid about 150,000 for 50 samples. And the one here on it has 3 parts. That's why it's called Poseidon, because Poseidon has a trident. If you've ever been to Bologna, there's a statue of him with its trident. So it has 3 parts. That makes sort of sense. So this part is a Palpissimo system. Here is an Ariane, the first Ariane implementation. And at the bottom, there's an independent machine learning accelerator. We got 50 chips for 150K. And once you manufacture the chips, you can also ask them to be bonded in a package so that you can easily work with them, because naked dies are kind of annoying to to work. So you provide a bonding diagram, you tell them how you want these pins to be connected, and 30 out of 50 chips were packaged. So what happens? So we are now zooming to the right-hand side, and look here. There's a pad that is not bonded. So what happened there? Well, we skipped one pad. So while we were sending them the description, instead of going like pad 16, 17, 18, oops, we made a switch. And every one of those wires are actually going upwards, shifted by one on that side. The other sides are okay. The problem is VDD and ground are one after another. So once you shift it, the VDD on that part is connected to the common ground, and causes all sorts of shorts between VDD and ground. This is pretty much catastrophic. So if it was this chip is ruined. However, fortunately, we still had those 20 unpackaged dies, and we were able to bond the chip to fresh packages, this time correctly, and we could use them and we can measure them perfectly, so there were no issues. It's normally, we would use about 10 to 15 chips to characterize it, so the number even wasn't a big deal. It was just loss of time, obviously, because you are very happy, you put it on the tester, nothing works, you're looking, debugging, and of all the things, of all the 80 million transistors that are in there, all the design decisions and everything, it was a manual piece of work where you are sending a document saying, please bond it like this, that had the mistake that could have caused the entire thing to fail. Now, this was the bad. What is the ugly? This is the reset problem of Urania. Urania is one of our recent 65 nanometer chips. It has 2 pulp clusters, so it's a multi-cluster system. Each one of them has 4 RISC-V cores, trans-precision FPU, 64 kilobyte banks, 64 kilobyte TCDM, and an Ariane host processor. So the bottom is the host processor. And in addition to that, we had a collaboration. This was as part of a project Opracom, and our partner there, Kaiserslautern, provided a Dram controller and PHY, which you can see all around here, that was on this chip. So what happened? Well, the chip has many modules. So the Ariane core, the DDR interface, and the clusters. But the reset going to the cluster part is stuck to 0. This is a design flow mistake. There are some other control signals that are stuck, which is the one that is affected are the clusters. Ariane is actually working fine, but some other issues are preventing from it to work at, let's say, properly. So it has some issues with its memory. Fortunately for us, the DDR interface is functional. So this was the major addition there that we wanted to test. So that one is actually working fine. In closing, I want to say IC design is very tricky and demands attention. Even the simplest things can derail a very complex chip. So a copy-paste error, like we saw in a bonding diagram, a mistake in the way reset is being handled, and the entire chip, months of work is going away. And fixing them is not always so easy. Sometimes you are lucky you have enough resources in the chip to still get the numbers you would want to get out of it. That is possible. Academic research chips are not industrial products. They are designed to test and verify ideas. They are not for mass production, so none of our chips are meant for being produced. You would need much more effort in DFT and verification to make a successful product. And this is where the additions of groups like Chips Alliance, Open Hardware Group, Low Risk come into play, because they have this experience and they are adding these things on top of what we already have, so that our good work is getting better and is more useful for the rest of the world. So experience is key in IC design. You make these mistakes and you learn from these mistakes. Actually, the one working chip is not the key thing. It was all the mistakes we made in the first 10 ones where we learned, and some of them you learn the hard way. And these mistakes stay with you, or the lessons stay with you and help you for your future designs. This is also why having so many designs is, in a way, important for us. So I hope this was helpful or fun for you. We covered the basics of RISC-V, explained the ISA, had examples of implementation, talked about advanced cores and concepts. We talked about building open source systems around RISC-V, showed the main concepts, and talked about our ICs. You can find all pulp related information on the GitHub page. our webpage is actually being kept pretty active with presentations and all the papers. And we try to maintain a fun and active Twitter page. So most of our publications chips, we talk about them, how things are going. So please do that. I am done, and now I can try to see what questions there are or ask help of Luca to answer them. Let me see, Q&A. Yeah, so I see a question by Drew. Do you think pulp will use SkyWater 130 nanometer? It disappeared. Luca answered it. Let me just say a few words because it's very up to date. The SkyWater Open PDK, it's very exciting, you know. It's good. One company had to start, the others will probably follow. We don't know how, I mean, we didn't really start, but already yesterday I had some interest from students and we are looking forward to try it out. Why not? I mean, it's a great story. So what we need is also to find some manpower. And yesterday night I was chatting with a student who was interested in doing something around that. Other open questions?
I think we have exhausted the students. So no open questions. Perfect.
That's good, or people are hungry. That's the other thing. So I'll wait another minute, but thanks for all for joining. Last chance for questions. There was a question. Does the company mean AVV? That's a good one, actually. AVV demonstration board, right? ASEA Brown and Bowery. No, this is automatic body biasing. That is true. Sometimes when you are in your own world, you just concentrate on your own acronyms. Okay. Thanks a lot from the Pulp team, also from Bianca de Ver.
Okay, bye-bye, everybody.